Hello. So, how's everyone doing? So, I wanted to today to talk to you a bit about data-oriented design for business applications and not games. And the reason for this is that there's many lectures on the web actually discussing data-oriented design, but in the context of games. So, they're gonna talk about any component systems and how to like manipulate vectors, how to do these sorts of operations on like numeric data. And there's not really a lot of materials how to apply this approach into your just business apps and applications in general. So this lecture is actually I just want to address this problem using this lecture. So I'm gonna talk about data-oriented design, what it is. I'm gonna actually talk about processor and cache, how they're designed, how they're like related to the problem, to the like data-oriented design in general. We're gonna look at some real examples, and these real examples will actually show us how to use array of structs of arrays, and a hybrid approach. We're gonna do some SIMD instructions as well, and we're gonna move to like handling text because, like I said, most of the time when you see these lectures or read about data and design, it's mostly in the context of games, and games usually most of the time don't really handle a lot of like textual data, which is actually the opposite what business applications have to do. Most of the time they have to actually wrangle a lot of like textual data and handle that. So we're going to look at some real examples how to apply the data approach in handling text. But before we begin, let's talk about what this lecture really is, who is it for, and how it's structured. So first of all, there are actually two versions of this lecture. So one was super technical and the other one is super practical, which is this one. And it's a bit like simplified. The terminology in this one is more simplified. It's a bit shorter, and the reason for this is that I wanted to do like an introductory lecture first for like people with just programming skills. The example is going to be here in .NET, and yeah, so if this actually works, there's going to be like more lectures around data-oriented design, possibly like more in-depth talks how cache works, what's false sharing, what is data dependency, and all of these like things, right? So let's talk about me. What are my credentials? So currently I'm employed as an R&I director. I manage research teams, like small research teams. I'm a performance freak. I like robust applications. I like stuff that works. I like building fast things that are actually responsive and bug free. And what I'm doing right now is I'm building an actual index for files where we do like mass data ranking. So you have to handle a lot of text. We calculate statistics, we run models, we do a lot of like stuff with files and different types of files. So that actually is one of the use cases where data-oriented approach actually makes sense. But what really is data-oriented design, right? So data-oriented design is actually something that is a bit opposite object-oriented design. If you sort of had that be like used data-oriented object-oriented design in the past. So object-oriented design will actually try to model your problem, or much model the world using objects. These objects will have like dependencies or relationships to each other. They're gonna have certain functionalities, methods, and functions in them in order to like provide utility. But data-oriented design will actually not have that at all, or most of the time this will not be a data-oriented approach. So data-oriented approach actually is more focused on algorithms and how these algorithms access and change and update and manipulate the data in general. So things like data dependencies, data access patterns, data alignment, and the algorithm itself will be the most important things, not so much like relationships between different objects. But what's the benefit of that, right? So the benefit is that this can actually lead to a pretty dramatic increase in performance, because if this is applied correctly, this will be like machine friendly, and our performance should like increase greatly. So that's the first benefit. The second benefit is that most of the time, if you're going into the data-oriented approach, you're gonna end up with simpler objects, simple relationships, and the system will be in general more clean. And hopefully I'm going to convince you that this is true. So let's look at some sample functions in order to understand better what we're dealing with here. So we have two programs, or two functions much rather. So what we have here is just a big array which is sort of laid out as a big matrix. And what these two functions do is that they're gonna go cell by cell, and they will just increment the value, because that array is an array of int, so just numbers, right? The first one will do it by rows, so it will increment each row and then move to another column. And the columns version will increment each column and then move to another row. So in terms of like reads and writes, they are equivalent. So it's the same amounts of reads and writes between these two functions, right? So I'm just wondering if you know which one will execute faster, because they should be more or less the same, right? But that's not really true. So we're gonna answer that in a bit, but in order to like fully understand what's happening here, we have to see how the processor and cache are designed. And this is, like I said, a simplified version of this. This is like an artist impression, where each CPU will have multiple cores. Each of these cores usually has registers, execution units, and caches. And there's multiple levels of these caches. So here on this sort of example, we have L1, L2, and a shared cache, which is L3 cache. So what are these caches and how they actually structured? So they're actually structured in like units. And these units are usually called lines, and these lines are composed in a set, and there's multiple sets within each level of the cache. So the actual important thing here is to understand that a line, for example, it's like a 64-byte line. So each time you do sort of, you try to access your data from like the memory, it's gonna get preloaded into one of these lines. And we have something here that's called a prefetcher. So if your data access patterns, so actually the stuff that you sort of try to read and write from memory, are predictable, the processor will actually try and preload all of your data into caches, if that actually makes sense and there is sufficient size for it and stuff like that. So let's look at actual like performance when it comes to accessing data. So registers are actually almost cost-free. There's no point in like telling what the cost is, because it's really tiny. Then we have the L1 cache, which is around 3 cycles. Then we have the L2, which is 20 cycles or more, L3, which is 50 or more, and then we have the main memory, which is more than 200 cycles. Usually it's gonna be like in the thousands. And then we have like the disk, but that's so slow that it would just fall off this graph to the side, and it's like light years, right? This performance is light years as compared to like disk, right? So there's no point in actually looking at that. So let's look at our like sample object-oriented graph, what it might look like. So we have an interface here that we inherit from, and this object A has like B, and that object has something else, right? We might have like an abstract or virtual class that might have multiple implementations, and this is what you're going to typically find in like the object-oriented systems. There's going to be some functionality here, there's going to be some data here, and it's going to be like a big graph. most of the time. And in like complex object-oriented systems, what you usually see is that these graphs will be like very deep, right? They're not going to be specifically wide, but they're going to be deep. So it's going to be like a deep tree most of the time. So how does this actually look in memory? So it might look something like this. So we have objects, they're sort of, this data is sort of fragmented because we don't have immediate access to all of these things. So if we wanted to read from D, for example, we would have to go from A to B and then to D. And there's someone else's data actually in between that because, well, it just happens. So like objects are references to each other, so they might be in a different place, right? And in like C# and Java and other garbage collected systems, it's actually really difficult to reason about memory layouts because we have garbage collection. And garbage collection actually has most of the time an algorithm called mark and sweep and compact. So this data will move all the time. Your data might be like in a different place. So it's really hard to reason, but this is what it might actually look like. So if we wanted to just slightly convert it into a more data-oriented way, we would actually end up in a memory that's not really fragmented. So we would have all of our stuff close together, and we could access this data in a sequential fashion, first of all. Second of all, we would like to have like simple objects and simple stuff. So certain things probably could be collapsed into like simple structures, so that data access would be even quicker, and relevant stuff would be close together and unrelevant stuff would be somewhere else. Okay, so moving on to a more like practical example, we have a object-oriented graph here. So we have a like a transaction. It has an ID title. It has some transaction info. Maybe it has some date time. It has some functionality in the form of the send method here, and possibly these could have other functionalities as well. That's not a problem, right? So this is our like typical, this is one of the ways that you can structure this using the object-oriented approach, right? But if we wanted to shift just slightly for now into the more data-oriented approach, we would like it to have just plain old data. So we would have, for example, a struct here, and that would have a bunch of fields that we usually operate on, and the rest of the fields will be somewhere else. Or we could actually have like disjointed objects and stuff like that, right? So there's gonna be like simple fields, no methods, just the data that we're trying to operate on, no complex relationships between the objects, and that's just it, right? So, but the interesting bit here is that probably most like object-oriented people, and especially object-oriented people that are really hardcore, are gonna say that this is bad because this is first of all, it's an anti-pattern because we have objects with just data, they have no functionality. This is like an anemic model. That's a problem, right? And now the second problem is, why don't we have properties? And that's going to be, actually, this problem is mostly specific to like high-level languages like .NET, Java, and others. Not all of them, really. But .NET people will just ask, why no properties? This is like real bad. This whole concept like smells. It's probably not very good, right? So I'm going to argue that no, it's not bad. It's actually good, first of all. And second of all, so first let's maybe address the anemic model. So that there's actually a lot of discussions around that, and not all people, myself included, actually think that this is bad. If you have like very simple objects, record almost like objects, right? The system becomes really simple if you structure it correctly. So that's first of all, right? Second of all, no properties, right? So what's the problem with that? So the problem with properties, and again, this is going to vary from language to language, but I'm just like trying to approach this from a like C# platform or these like Java platforms, high level platforms, right? So most of the time what you're going to see is that properties are just a lot of typing for nothing, really. So what happens here in this example? So we have two fields. One is a property with a backing field, and the second one is just a field. So first of all, incrementing your field is going to be faster. Second of all, if you want to increment a property, you'll have to look up a method table and then find that field and increment that field. So that's the first one, right? It's slower. The data data access pattern actually changes because we have to access the property first. And there's a couple of more problems because, like I said, it's just a lot of typing for nothing. You have to auto implement these getters and setters, and say that you actually want to use some like functionality here in the getter or in the setter, right? So you're gonna run into problems because no one actually expects you to do that. And if you do some computation there, people are gonna yell at you, and rightfully so, because it's not very apparent that this is gonna do some calculation or even caching or stuff like that. So no one will actually test it like that, and that's gonna be a problem. All right, so how to actually structure the transaction in a data-oriented way where you have all of this data. So we could do something that we call a hot-cold split. So for example, if we just care about the amount and who to send it to, right? We could actually settle on these fields, and the rest of the data, so like transaction info, we can put somewhere else, or we can put close together using struct, or we can just say that it's going to be a class, it's going to be a reference. We don't really care about this, so it can be somewhere else. We just don't care for now. So we're just operating on a couple of fields, and this is what we're interested in. So going back to my question about these two programs, right? So which one will execute faster? And hopefully you sort of have the idea which one it is, but let's actually look at how it actually behaves. So this is the performance result. So the ROS version should execute a lot faster than the calls version, but let's actually see what happens. So in the ROS version, and if you recall the cache line discussions, right? So in the ROS version, what we're actually doing is we're loading the data into the cache line and we're incrementing each data point. Then we're gonna load another line and do the same thing. So it's a very simple and predictable data access pattern. So we're gonna get some help from the processor, and we're gonna it's gonna preload all of our data into cache, and we're just gonna write to cache without like going to main memory and stuff, right? And what happens really in the columns version? So we're gonna load a single value, then we're gonna increment, then we're gonna throw that entire cache line away, we're gonna load another one, increment, throw that away, load another one, increment, and throw that away. That's a problem, right? So this is a big problem. And to actually verify that this sort of thing happens, let's actually test this. So a couple of things about testing. So first of all, I'm not going to use the benchmark dotnet because that's way too slow. It's really hard to actually test code that has data access patterns, because that actually can cross like process boundaries. And since this is a single process that actually coordinates different processes, we're going to have problems. But that's not the biggest like issue here. The biggest issue here that it's just too slow. And what we're going to settle for is a very simple function that actually measures performance. It has like a quick warm-up phase to, not look at like, cold data. So we want to warm this up first, and then we're just going to run. So this is not the best way to test, but it's pretty fast, so you can sort of execute this a lot of times without problems. And in these examples, you should actually see the results of that, and it should be apparent which one is faster. All right, so going back to the example, we have the calls version and the ROS version. And it's the same code as we had on the slide. So it's the rows version will actually increment by rows. The calls version will increment by columns. Okay, so let's run it in release mode without the debugger attached, and let's see the results. Okay, so it took 1 second, and let's actually make it a big, just a bit bigger. So what we have here is 1 second, not so bad, right? But we don't have a reference. So let's try out the ROS version. As you can probably see, it's better. It's around 10 times better on this machine. So I hope that I've convinced you that this is actually what's happening. And let's actually move to some other examples, which are actually examples that we sort of have to deal with in our work. So this is a PO file, and it's a transaction file where we have to do some data wrangling around it. So first of all, it's a flat file. It's a structure, and it has, so the first line has an ID. The second one is a datetime, which is not an ISO datetime. It's like a custom format datetime. Then we have the amount, which is like either a double or decimal value. For simplicity, I just chose simple values here. And then we're gonna have something that we call a note, and this is text that can be multi-line. So this actually tells you what the transaction was for, what this money was actually spent for. And what we want to do here is, first of all, we want to create a parser which parses this file and gives us these transactions. And second of all, we want to do some interesting operations on these transactions because we have to usually do them. And we usually resort to two things. So first of all, what we usually do is we have to sum these amounts in the file. And second of all, what we have to do, because like I said, we do a lot of data wrangling, so we're actually very interested in the note field here. And we have to do a bunch of things. So first of all, we have to normalize this. And second of all, and which is the most important bit actually, is we have to split this text to words, and then we're gonna do some statistics on it. So let's actually see how we would approach this from a data-oriented way and the object-oriented way. So a typical thing which happens is if we have a new employee in our company, a typical thing that happens is that any developer, when given a problem to actually implement a parser, will actually resort to regular expressions. So we started with we had one problem, right? Now we have two problems probably. So let's actually, let's actually implement that and see what happens. So our regex parser might look like this. So we're going to actually capture the entire line into separate groups, and we're just going to run it into this. We're just going to write into this PO line object here. Nothing really fancy. And yeah, that's it. Basically, that's it. So we're gonna, after this is done, we're gonna have a bunch of transaction lines, and we're not gonna measure the performance of the parser so much rather we're gonna measure the performance of these two operations. So first of all, summing over the amount field, and second of all, splitting the note into words. So that's not very good, but let's actually see how it performs. So almost 400 milliseconds. Again, we have no reference. Is it fast or slow? Let's actually move to a better version, I would call that. So maybe we don't want to use regular expressions because this is simple, right? We don't really have very complicated things. And even if we do have complicated things, I would still opt for implementing a lexer or a tokenizer, and then possibly a parser on top of that, because that's going to be usually more simple and fast. But still, what we have here is a state machine where we just say that these have to happen in a certain order, right? And if we stumble upon something like that, so we know that first of all we have the ID, the next is going to be a date time, then we're going to have the amount, and then we're going to have the note. And if we have an empty line, that means that this transaction is over, and we're going to read the next transaction. So this is a pretty simple, pretty robust parser. Like I said, nothing fancy happens here. The object, of course, is the same. So unsurprisingly, when we run it, we should have the same results, right? So this is just a sum over the amount. And yeah, as you can probably tell, it's mostly the same performance. Okay, so now how would we start to refactor this into a more data-oriented way? So first of all, let's do a very simple change, and let's change the class to a struct. Let's remove all the properties, and let's just go with this state machine parser that we had before. And that's it. Let's just see if this is good enough, right? Well, it's around 3 times slower. Why is that? Perhaps we need more refactoring. Perhaps this is not as easy as we thought it was, right? So I'm going to answer that right now and tell you that that's not really what's happening, but let's continue our refactoring journey first. Okay, so maybe what we have to do is we have to split the data a bit, because we're actually interested in this. So this could be actually a class, because we don't care about this at all. Maybe we could pack this structure differently in order to fill the entire cache line. But in this example, we're going to be still misaligned, so that's not really helpful. Maybe with different paddings, because we have 8 byte double here, so everything is going to be padded to 8. But that's not really a problem, I think, for now. So let's just make this change and see if this actually improved, because like I said, we were around 3 times slower. Okay, so it did improve a bit, but we're now 2.5 times slower. So that's not it. So let's try something else. Let's actually go into the hot code split. So let's just say that we're only interested in the amount. Again, this should be probably a class, but whatever. And let's run it like that, right? It didn't improve at all. So why is that? The reason for this is, if we look at the parser that we started with, which is the object-oriented one that we're using, we're just changing this, right? The reason for this is we actually have a list here, and in order to sum over the amount, what we're doing is we're actually using the for each loop, which is an iterator. And that's a problem. Sorry, that's actually an enumerator that has the iterator, but whatever, right? That's a problem. And why is that? First of all, the enumerator is a struct in itself, but we can deal with that. That's not the actual problem. But the second problem, the actual real problem here in this case, is that we're actually using the struct, and we're copying it to a local variable, and then we're going to pass it to the for each loop, right? So what we're actually doing is we're operating on a copy. So we're doing a lot of copies, and that's it. That's why we're very, very slow. So how do we fix that? Well, we could create a different kind of enumerator, but since this is a list, we don't actually have an opportunity to do that. We have to implement our own. And like I said, this is just an introductory data-oriented design lecture, so let's not do that perhaps. Let's do that maybe in some different lecture. there is a simple way how to handle that. We should use arrays. And arrays actually don't have an enumerator, and if we're operating on the indexer of the array directly, we're not making a defensive copy, and everything is fine. We could do that with lists as well, but I just didn't want to do it because that's really terrible design. So let's actually look at how we would fix this. We have the array. We have like pre-allocated the size, but we have the index here, which will tell us how many of these we actually used, and we're just going to operate on that. So every single like refactoring that we did, we have to redo with like instead of lists, we have to use arrays. And let's see if it actually improved. And let me just remind you that it was around 350 milliseconds to use the object-oriented parser. Now it's 93. This is the split version, 92. It's like statistical error for me. And 92. So this obviously works. The split of the data didn't work because this example is like too simplified, and we're using structs. We should probably use classes. But as you can hopefully see, now the data-oriented approach is really, really fast as compared to the object-oriented approach, which is this one, right? So how much times it's faster? It's like 5 or 6 times? No, it's around 5 times faster, right? Okay, so we know that this works, but we're still not done because that's a very simple thing. So right now we have an array of structs, but let's actually flip this around and let's just say what would happen if we won't, since we're trying to operate on just a single field right now, let's maybe flip this around, because what we're trying to do is we try to pack as many of these amount values in a single cache line as possible. Well, how to do that even more efficiently? Well, we could actually settle for a struct of arrays instead of arrays of structs. So we have a single struct here and we have a bunch of arrays, and our indexer in all of these arrays will actually determine which transaction it is. So again, the parser remains mostly the same. What's changed is the underlying like data structure that we have here to represent our transactions. And now if we're trying to sum over this field, we have a simple array of values, and they're gonna be like, you know, laid out perfectly in the cache line. They're gonna fill the entire cache line. They should be preloaded, and it should be all better. But this is kind of like a, you know, not very friendly. Well, depends who you ask, but it's a real big change, right? But let's actually see how if it actually works even faster. So we have the structs of arrays. It is faster, but it's only a bit faster. So yeah, I mean, it's gonna be faster, but it's gonna be just a tiny bit faster. But there's ways to make it even faster if you wanted to, because if we're gonna do this design, there's more benefits. Because if you think about stuff like how to actually make it faster, because right now we're getting a single value, we're actually summing this value up, then we're gonna move to the next one and the next one and so on, right? So there's a concept called a SIMD instructions in like the modern processors, which actually means single instruction multiple data. So instead of like just grabbing a single value, we can grab a bunch of values and sum them together using a single operation. So that should be faster. And we can actually perfectly do that with structs, like arrays of structs. That's not a problem. The problem here is if you have this sort of operation that actually tries to do like sum an entire vector at the same time, what you're really interested in is how to fill up that vector as fast as possible. And in order to be able to do that, you just don't want to jump between like memory. What you actually would want to do is to have a single memory block which you can read and pump that data in. So this is exactly what we're going to do. So we have this method here, which is some amount. It's going to take the struct and it's going to preload this vector here with data, and it's going to sum over this vector. So it's like in the case of the amount, that's actually 64 bits, so we can actually do two operations at the same time. So we can grab two values and sum them at the same time in this like specific case. There's actually bigger vectors, but I just opted for this one. They're dependent on the processor architecture in this case. So let's actually see how this performs. So it's a lot faster. So it's twice the speed of the non-SIMD way. So as you can hopefully see there, now we have, if we're gonna go into the SOA approach, which is the struct of arrays, we have the flexibility to make it even faster if you want, right? And what else is interesting about the SOA approach is that we don't have to have this like word structure here, again, depending on who you ask. If we wanted to operate on structures like record fields or on objects, we could actually have this, for example, datetime could be a single object, and it could be an array of datetime objects. So this is like a hybrid approach, so it's a struct of arrays of structs, and which one you should use, right? So you should use, you should actually merge like fields into structs together if you're operating on them. So if you, for example, didn't want to sum over the amount, but sum over the date time, or like calculate the date time offset, you would need these two fields. So you would create a struct which actually loads stuff into these vectors, for example, right? And actually operates on this data block. All right, so we actually can sum real fast over the amount, but like I said, that's not the most important thing. The most important thing in these parsers actually is the ability to operate on text. So let's look at another example that we have here. So usually what we want to do is we want to normalize the data and split it into words. And for the sake of like this lecture, I'm gonna resort to something real simple. As you can imagine, you have the note field in each of these transactions. And what we're gonna do is we're gonna take the single note, we're gonna split it, and we're gonna just put it into this array, right? And hopefully you can imagine that down the line somewhere, we're gonna calculate statistics, different kinds of statistics on these words. Okay, so let's see how it behaves in the object-oriented way. And this could be slow. This operation could be really, really slow. We have to wait a while, but hopefully we're gonna see some result. Yeah, so it took 4 seconds. And let's now actually try to refactor this into a more data-oriented approach. So how we would actually do it, because we have an array of nodes, which is a problem because ideally we would want to operate on like one piece of memory which has all of the nodes. But here we just have an array of strings, and each string is an actual reference. So we actually have to do, first of all, we have to locate the reference, and then we have to actually get that pointer and actually follow that pointer to the actual array of like, characters. So that's not ideal. And there's ways to solve this problem, but ideally we wanted to use the simplest things possible in our toolbox, we don't want to like re-implement strings. We don't want to operate on like byte arrays because of encodings and stuff like that. We want to use like simple things to solve this problem and to solve it really like quickly and use our like data-oriented approach. So if we wanted to, for example, have a single memory block, we could use a string builder, which would be called all nodes. And what we would have to do now is to actually say where like the node of a transaction starts and begins. So we have a node offset here, which actually says where are like the breaks between the nodes, right? So we have a single memory block, quote unquote single memory block, because this is not a single memory block. This is actually a linked list of a couple of buffers. But for now, it's going to be good enough. We could actually make it better, but like I said, let's resort to simple things that are in our toolbox already. We don't want to implement our own like complicated data structures yet. So let's use this idea, and again, the parser didn't change, so let's use this idea and let's see how it actually performs. So now what we're going to do is we're actually going to take this and we're going to turn it into a string, and then we're just going to split. All right, so the last one took 4 seconds, and let's see how long this will take. So from 4.5 seconds, I believe, to 2.5-ish seconds. So that's not bad. And there's actually more that we can do, because like I said, we have to normalize the text in a when we actually begin work. So as you might imagine, we would like to do the to-lower operation here. And with the object-oriented approach, of course, we can have all nodes as well. We can have that string builder. But since we know how to operate on SIMD instructions, and we know that if we have a single memory block, then we can load stuff into vectors real quick. So let's actually see how to do that in the like a SIMD way. So again, we have all of the nodes. So this is like all of the nodes here. And what we're gonna do is we're actually gonna do a to-lower operation. And this is like the, so again, we're loading stuff. We're doing like a simple bit operation here, and we have the to-lower value. And we're gonna store it into the same memory block. We could have something else here, but let's just do it into the same memory, because that might be, depending on what's your use case, it might be actually good or bad decision. So let's actually measure the to-lower in a object-oriented way. 350 milliseconds. And let's actually test that in a data-oriented way using SIMD instructions. So it's 2.5 times faster, probably, right? Okay, so in terms of the examples, that's probably it. Hopefully you can see that, and let's actually, yeah, so this is all of the results on a single slide using benchmark.net, and as you can see, the structs of arrays using SIMD instructions is the fastest one. It's not really difficult to be able to go from a properly designed like object-oriented parser into a properly designed data-oriented parser with SIMD instructions on top. We could, for example, stop here, right? That wouldn't be a problem because this is very stable. It utilizes memory in a very efficient way. Probably like the standard deviation and error rate are really slow. Not really slow, but really low. And that's because we're not actually triggering a lot of garbage collection as well. So there's a lot of benefits to like using the data-oriented approach. And like I said, if we split this into like simple data structures, just that have data without really relationships between each other, you can end up with a simpler system. Sometimes you have to have relationships, but you can mold them in this very data-oriented approach, so they're not going to be in the same memory, or sometimes they're going to be in the same memory. That actually depends on what your use case is. Of course, there's a lot of more. There's like heaps more, and this is like an introductory course to data-oriented design in .NET, and hopefully there's gonna be time, and there's gonna be like people that want to see more, because this can be approached in like multitudes of way, from like a currency perspective, non-reactive perspective, architecture perspective. So there's a lot of topics that this one didn't cover. But yeah, hopefully, all in all, hopefully you have a better picture what data-oriented design is, and if you should actually apply this, and if you can see that it's, at least if it's not cleaner, it's at least a lot of times faster. Okay, so that's it for the lecture. If you have questions, remarks, comments, put them in the comment sections on YouTube. And yeah, hopefully we're gonna see each other next time. So thanks, bye.